Okay, a couple of comments on the test. Uh, Results weren't as good as I would have expected from the homework that I saw. So I made up this sheet that we'll be talking about a little bit today and, you make some revisions to it and so forth. Because there's really a few things you got to know, and most of them are on that sheet. Then you got to be able to use them. So it's kind of like you got this pile of stuff that can be constructed into a beautiful palace. And you get into that pile and maybe you construct a shack. Okay. You got the pieces. Maybe you don't know how to use the tools. Maybe you're trying to screw things in with a hammer. Stuff like that. That's an analogy to a lot of what I saw on the test, and on most tests. So we'll be talking about that. I haven't put grades on them yet. I will say, everybody's going to get at least a low passing grade. Okay. And I don't think anybody's got an A. And the way I'm going to have to grade the test, rather than grade them point by point on the problem, I'll grade it two ways. Point by point on the problems, and then a list of things that you ought to know. How much of it did you know? And whichever score comes out higher, that'll be your score. That makes sense? Okay. So I'll get back to you on that. I should be able to get into that better this afternoon. I didn't get into it. I thought I was going to be able to grade things while I was in Charlottesville. But it turned out to just be a really beautiful 60-degree day with sunshine. So I just took an hour walk. I needed to clear my brain. Then when I got back and thought my brain was clear, it wasn't. I've been wrestling all weekend with just how to address it. Okay, how to get everything on the track it needs to be in the next 5 or 6 weeks. Okay, how to bring all this stuff together and then build on it. Just examples. I saw a lot of cases where people were falling back on the equations of uniformly accelerated motion for a spring. Well, the motion of a spring is not uniformly accelerated. So you just can't use the equations of uniformly accelerated motion. It's the thing most people are most familiar with and do best in. People do pretty well with the equations of uniformly accelerated motion. But when you get beyond that, sometimes you got to use energy and you don't really have a choice. Sometimes you got to, well, we didn't have to use momentum, energy conservation and stuff like that. And it got muddled in many cases. You can see bits and pieces there, but people weren't necessarily saying what the connection needed to be. So we're going to be working on that as well as progressing forward. I guess forward was redundant. If you progress, you are going forward. So you wouldn't say progressing forward. So I wouldn't not say that. Okay. Kinetic energy of the magnets in the end is 0.3 joules. Okay. So you got 400 grams of magnets in the end, not 200, but you did it for 200, you got it right. That's, like I say, it's guaranteed to crash your spacecraft into Mars and cost multiple billions of dollars. But as engineers, why would you have to worry about something? Oh yeah, you're engineers. As physicists, you don't really worry much about it. You just don't, take the square root of 2, divide by the square root of 2 and get the right answer. But okay. What you need to see is The kinetic energy is 1/2 mv squared, which everybody knows. Nobody messed that up. Okay, you just didn't use it necessarily when you needed to. And some people did, so, but there were a lot of cases where you didn't. Okay, anyhow, that equals 0.3 joules. And let's just do this symbolically. Joules a kilogram meter squared per second squared. So I'm going to write that unit in over 0.4 kilograms. As I saw everybody, they knew what 200 grams was in kilograms. So I'm sure you would have known what 400 grams is. Okay. See, that's not going to be a problem. Well, the kilograms divides the kilograms. You get 0.6 divided by 0.4. It's the square root of 1.5 meters squared per second squared, which is approximately 1.23 meters per second. I'm not sure about the 3 on that, but something like that. Okay. Measured probably close to 1.22, maybe even 1.21 something. Anyhow, there it is. Okay, so that was pretty easy. And then a 10 gram Okay, I'm sorry, I said descends distance delta y. I want to say it a little more. You're going to say it changes vertical position by delta y. Okay. Get up on a frosty morning. Try to get up kind of right as the sun's rising, and you can see the area. So that's U subgrav. It's gravitational potential energy. Okay. But you can really see a lot this last year. Also have my laser infrared thermometer. Another great tool for what is likely the negatively affected or positively affected. So consider that in terms of how much light do I get when, and that's the big driving factor. So the change in gravitational potential energy is negative mg delta y. How does that play into where I might throw crops? And delta y is negative, so that would be positive. So it's got to be the negative of mg delta y. And air pocket might not be a great spot to grow more season crops. Anytime out of the regular season. So we'll just say mg delta y. Well, so equal and opposite to the work done by gravity. Okay. Right. So think about how if that frost temperature is at 32 degrees, which I think that's what we finished Saturday night, Friday night. But we could say this. Now, how does that help? Are we talking about the potential energy? Because we're assuming no dissipative forces. I don't have room to write the rest of it out here, so I'll just move this over a little bit. Block the board while I write it over here. Let's see if I can. No, take it back and go right over here. Sorry. And I've got clear on my screen. I can't tell where I am. So I'm going to fix that. Okay. I should have help in the room here. Okay, the physics of it is. Assume no non-conservative forces. Now, this is like the system that you're very familiar with. You assume friction is zero, but we'll contradict that in lab later. Okay, we'll figure out what the friction and other non-conservative forces amount to. So, if we assume implicitly that we start this thing from rest, because how far would this have to descend to provide this kinetic energy? That means we would be starting with zero kinetic energy and building it through the work done by the descending mass. So right here is our conservation of energy equation. People didn't use conservation of energy on the whole in the test. Okay, some people did. Some people attempted to, but made little errors and details. So it's a pretty mixed bag, but I was looking to see better use of conservation of energy and recognize when it's supposed to be there. Okay. One comment on preparing for test, digressing from this problem a little bit. If you see it in the chapter problems, you're going to be keyed in to the idea of conservation of energy. And you're going to do it sometimes more or less by rote, more or less by habit, without really understanding it well enough to pull it out of memory on a test. Does that make sense? You got to think about how to write things out so that you understand them. You should write more maybe about the principles. Okay. Now another digression. I looked at I didn't have a whole lot of time this morning. And didn't want to start on it until I got all or almost all of the homework. Okay. Which came in, I think got almost all of it by before midnight last night. So I was able to look at it this morning. And I was able to look at the chapter 9 problems, make some notes on them. So I emailed those. If you looked about them, but you've been busy all morning, you might not have looked, but they should be there. And those problems on the whole look pretty good. And I found myself wishing people would write out a little more what the principle is. And that's what we're going to talk about in relation to this handout. Okay. Okay, so anyhow, back to this. This situation here is simple. These things get some kinetic energy. Where they get it from the descending mass. How far does the mass have to descend to provide that kinetic energy? Well, it has to descend far enough that its potential energy loss is equal to the kinetic energy gain. So we got delta Y equals delta U grav over mg.
So we have multiple genera in one family. And there are some cases where the family there's only one genus. But they were originally put together and classified based on their reproductive characteristics. Before following shape, size, those characteristics. But today they're reclassifying them by.
I've got it there somewhere.
So there's lots of reasons why we might.
0.3 joules.
One way is to straightway and narrow down your.
Got so much stuff written there. It isn't that much. But for a minute there, I was just unable to sort it out and find this. Okay, anyhow, you grab is
So
this.
as we go down, like our taxon,
So that,
we're getting more and more narrowed in on similar to their ability really to interbreed and gain similar characteristics. So we got genus, then we have the specific
and mg
epithet.
is 0.1
Is binomial.
kilogram.
That's what we're looking at. The family is good to know because it's like we can get there first, that's easier to get down here. So.
And of course, that's-
Specific epithet makes the species name behind it.
0.1 kilogram
And in fact,
times-
that it is universal. It's recognized, communicating with someone in China.
and it's 10 grams, so it's 0.01 kilogram.
As that point, we don't have to translate.
I'd already approximated this as 0.1 Newton, but then I wrote kilogram and confused myself. So write things out a little more carefully than I just did. Anyhow,
So that's our main.
this equals negative 0.3 joule over 0.1 kilograms. So that would be negative 3 meters. 0.3 joule over 0.1 Newton, which is 0.3 meters, because joule is a Newton meter, right?
So specific epithet is describing that.
And I guess,
So say. In the water lilies.
I'm gonna write an intermediate step here just to connect some units.
Yeah, it's white,
But I
so,
still see,
not only are they universal, they are also. Not in every case, in some cases, it's just describing a person honoring blackness. Something like
a
that.
joule's a Newton meter. Convenient to write it that way. We could write it as kilogram meter squared per second squared. And we have a kilogram meter per second squared here. We'd still get a meter either way when they go to fundamental units. But I'm just gonna write it as Newton meters over Newton.
In language, it's change. So
We get negative 3 meters.
those are my main reasons for us to use things.
That's our
You know,
delta y.
for us, this one, as we kind of go into our next phase,
I want to go on with this example a little bit because I want to get into
is,
all the way into conservation of angular momentum. Okay. So my next question is, what's the angular velocity of this system?
For those that are online. Tell us a little bit about what you started on.
Let's assume that we're not talking about the actual system there with the mass of the bar or the beam. Okay, let's just say the beam has negligible mass and we're just interested
This is what we use, right? So if I
in the moment of inertia of the
want white water lily,
rotating
I would not search for white water
the
lily.
magnets in their circular motion, which is rotation. Okay. So
All right.
the moment of inertia, well, start with angular velocity.
The variety. don't underline that, so I was just trying to say that portmanteau, two words combined to say folklore. So I'm sure there probably are some white water.
So what's the angular velocity of the rotating magnets assumed massless beam?
The problems that we get to when it comes to identifying plants is that it's or difficult and the water like some taxonomic
R, which is the distance of the magnets from center, is well, 30 centimeters.
variety is not necessarily you just make up all of that. Most people would accept, right? So there are rules around it, but they're rarely followed. So to get into the complexity of variety, get crazy. But
Well, omega is delta theta over delta t.
about like it gets popular.
Speed
Begonias. So we think about begonias.
is
There's a lot of them, right? There's
1.22 meters per second, I think.
But let's just say if we take like a particular
One revolution is 2 pi radians.
probably a mutation.
The displacement for a revolution is 2 pi times the radius,
Someone saw this patient and then they propagated it.
which is
Then they may have made it there.
60 pi centimeters. So I'm going to say that's approximately 190
Cargo. You heard that one
centimeters.
before? So it looks like a stamp, right? It resembles a cell, so it's that is the variety of begonia reds. So see that you get a whole lot. I would say red.
It's 190, excuse me, 190 centimeters over 1.22 meters per second. Which is around 1.5 seconds. So omega is approximately what? Delta theta, which is theta of 1 revolution, which is 2 pi radians. Two pi radians over 1.5 seconds is approximately 4 radians per second. That makes sense? Well, you can go to all this trouble because you know how far a revolution is. You can relate your speed around that arc to the rate at which you're going through angle around the arc. Okay? That's how you can relate your speed in meters per second, centimeters per second, whatever, to a number of radians per second. Easier.
Haven't figured out exactly what species is. But as each singular, it's one species. Those Virginia was what because there are multiple different heights that we
Is
can-
V equals R omega,
But we're not-
but that's a hard formula to remember because you never remember whether there's 2 pi in it or whether R is in the numerator, omega in the denominator, or what.
Flower color. for the same species.
Unless you understand what that means, which I've talked about before, but you really want to try to lock it in.
Right. And it's got-
R is
All right, Ed. Talk about Ed there. So we have that here. Umbrella. Umbrella is a good example.
the distance or length of the radius.
But what the heck does an X mean? X is hybrid.
Omega is,
Cross. And a lot of times, something with an X in it will become a full. Hybrids occur in nature with some plants,
how many?
but
You want to call it radians per second? I'm abbreviating it RAD, okay?
And some have more genetic.
But a radian is just equal to an arc distance, or corresponds to an arc distance equal to the radius. So this is how many radiuses there are in a second, how many radii in a second, and this is how long a radius is. So it's distance of the radius between times how many radians per second, or radii per second. So
That are cross bred together to make something that ideally has the choice quality of both of them. So, yeah, hybridization is a great tool that we use, and it's important to know in design.
radian per second is a radius per second in the sense of a radius of arc distance. Okay, radian is a radius of arc distance. End of argument. There's a simple reason for this if you understand a radian. Now, I've exhorted you to do that a number of times. Your life will be much simpler if you do. Okay? If you haven't already done it. If you've been working on it and it still hasn't popped in to your head in a way that you really understand it, keep thinking about it. Okay. That's the intuitive part of this. But of course, you could use that as a formula. And that equals,
All right, anything else on there that, we want to talk about or talk? Well, the sign of like.
30 centimeters.
Describing a color. Or lobelia syphilitica.
Times omega.
Describing a historical
And this,
hue.
omega is V over the radius.
Correct translation, Nova Anglia. Fraser, I know the Fraser Magnolia describes. Niculata, describing, that it is a mantle, so compare the powers.
And that gives you 4 radians per second. Now, how do you get radians out of centimeters per second divided by centimeters? Well, this is centimeters of arc. This is centimeters of radius. When you divide the distance along the arc by the radius, you get the number of radians. Which again, you understand very well if you understand radians very well. Otherwise, it's just kind of magic. You divide centimeters by centimeters, you get radians. But there's a reason for it, and it's worth understanding the reason. Not absolutely required if you understand that this gives you radians per second, even if you're a little fuzzy on why. It's okay. So I got a question, so let's see what it is.
In the family. Including like the turkey.
Okay, so we've seen, I think, the definition of moment of inertia is what you get when you add up all your MR squared. There are good reasons for that, and I'll kind of get to them in that sheet.
All right, well.
Okay. Moment inertias, some of them are squared. Um, I take little m to be the mass of a particle. Okay. Treating the magnets as particles, which is close but not quite right. For reasons we'll see. Not worrying about it right now. Just, treat them as particles, because most of the magnet, I mean, practically all the magnet is at 30 centimeters. That's between 28 and 32. 30 is an average, but you'd have to average the squares and stuff like that. Don't worry about that right now. Just assume that these are particles of mass 30, of mass 50 grams each, and there are 4 of them in each end. Okay, so the total mass of 8 of them is 400 grams. Okay. $400 grams times 30 centimeters squared. Well, that's 900 centimeters squared, and 900 times 400 is 360,000 grams centimeters squared. But a gram is a thousandth of a kilogram. So we could say that's 360 kilogram centimeters squared. A centimeter squared is a 10,000th of a meter squared. Centimeter is a hundredth of a meter. If you square that, you get a 10,000th of a meter squared. So we got to move the decimal over 5 places here. Now, the ways you can use conversion factors formally, but we move over decimal from here, 1, 2, 3. That would put it here. Then we got to go 4, 5. Okay. So this, unless I've screwed up the powers of 10 somehow, and I might have, keep an eye on me. Okay. But that seems about right. Okay, that's the moment of inertia of those 8 magnets at 30 centimeters from the axis of rotation. So your kinetic energy should be 1/2 I omega squared. Well, that's going to be one half of what 0036 kilogram meter squared times 4 radians per second quantity squared. 4 squared is 16. Half of that is 8. 8 times 30 is 240. 8 times 6 is 48. So that's 288 in this decimal place. And that comes out 0.0288 joules. No, that's not quite right, because 1.22 centimeters per second wasn't quite right. It's going to be somewhere between 1.21 and 1.23, I think. Maybe closest to 1.22, I don't know. But you got a little error there. And oh, And I've got a power of 10 error in there somewhere. Because that should come out 0.03 joules or 0.3 joules. Okay. And it didn't. So redo the calculation, think about what it means, do it carefully, and it'll come around full circle. Then you start thinking about why. Okay. Now we have talked about the fact that kinetic energy is 1/2 I omega squared. Okay. You good with that? I'm still not sure where in the world this thing went haywire, but I'm not going to worry about it. Okay. Well, okay, so this system, if the magnets are moving at the speed I said, has an angular velocity of about 4 radians per second, right? What's the direction of its angular velocity? Spinning in this plane here. And we'll say in this direction. What's the direction of the angular velocity? Okay, maybe you ought to review some of the things I tell you in class, but we're taking notes.
Counterclockwise?
Prominent things. Somebody in the hall is trying to talk to me again. I don't know. I don't know what's the matter with these people. Okay, so again, we're in what direction is associated with this motion? It's not this direction, it's not this direction, it's not this direction. This direction keeps changing. It's not one of the directions tangent to that circular path. There are infinitely many directions in which that mass is moving, okay? So we want the angular velocity. Now for this and another bunch of reasons, again, I'll remind you, don't forget it this time, okay? Right-hand rule, angular velocity is in this direction, okay? Make sense? Maybe not, but it works. You'll see how it works. And unfortunately, we're not probably going to be able to get all the way into precession. The precession of a top. You spin a top and it kind of rotates around this way. Okay. It's not too hard. Read it if you're interested, or ask me to explain it sometime. And I will, but we can't really take a lot of class time to develop it, but you're going to have everything you need to understand it. Okay. Because here's what you need. Okay. Okay. Now angular. Kinetic energy is 1/2 I omega squared. Is omega a vector? Well, darn right, omega is your angular velocity. It's a vector. I just told you what direction it has. Okay, and if it's spinning this way, then you got to turn your right hand around and stress my elbow, but there we go. Okay, this way could be either, because we've had this thing rotating. Usually, when it's rotating, I think I've seen more more clockwise than counterclockwise. So when you see this thing rotating, whatever direction you set it up in, you're going to want to think the angular velocity is this way or it's this way, or if the thing's on its side. I've got one right here. If I can hold on its side and rotate, it's got a spring on it. That's going to screw it up. Let's just do this. Okay. So if I rotate it like so, Well, my right hand goes in that direction and my thumb goes in the direction of the angular velocity, right? So, and that was counterclockwise if you look at it from where you're sitting. The angular velocity would be this way, and vice versa was rotating in the opposite direction. So every time you see something rotate, when you drive your car, think about the angular velocity of wheels. What is it? Well, it's perpendicular, you know. And if you're backing up, it's you're right. If your front wheels would have angular momentum to the right. If you were backing up, and if you're going forward, angular momentum to the left. Okay. Don't think about that too hard, or you'll drive off the road, so don't do that. All right, angular kinetic energy is this. Omega is a vector, but of course, when we write it without an arrow over it, it's a scalar. It's just the magnitude of the angular velocity. Now, on the sheet I gave you, I didn't have time because I finally decided this morning, what in the world am I going to do to get everybody on track with all the stuff we've done so far? And I had an hour, so I wrote this out and formatted it, everything but the boldface. So vectors are not in boldface here, so you're going to have to put arrows over them. Figure out what's a vector, what isn't, put arrows over them. Some advice. Okay, angular kinetic energy is this. Angular, just checking the time. Angular momentum, what do you think angular momentum is? Well, first of all, how does this compare with 1/2 mv squared? It's exactly the same form as 1/2 mv squared. V is your translational velocity, motion from one point to another, okay? And m is like your moment of inertia, okay? Analogous to your moment of inertia. So moment of inertia acts just like mass. Okay, angular momentum is what? If angular kinetic energy is 1/2 I omega squared, then by analogy with translational momentum, what would angular momentum be? Okay. So angular momentum is your book uses L, fairly standard, capital L symbol for angular momentum. It's I omega. And it's a vector. So the angular momentum, well, I is always a positive quantity. You don't have negative mass, you don't have negative moment of inertia. Moment of inertia, you add up mr squareds. R squared is always positive, mass is always positive, right? So I is always positive. So that the angular momentum is in the same direction as the angular velocity. Okay, well, that's an easy thing to calculate if you know the angular velocity. If I ask you what's the angular momentum of that system, you'd be able to answer me. Because we figured out that the moment of inertia is 0.0036 kilogram meter squared. Unless I had too many zeros, and I suspect maybe I did, since the way I was off on the final answer. Anyhow, there's your angular momentum. Okay. In a closed system, angular momentum is conserved for the same reason that momentum is conserved in a translational system. It's because whenever two particles interact, they exert equal and opposite forces in each other, so they have equal and opposite impulses, which means equal and opposite changes in momentum. So total change in momentum is always zero. If you have two things that are equal and opposite, you get zero. Okay? For an angular system interacting, for rotating systems interacting, you get equal and opposite changes in angular momentum. Because again, you have all forces are equal and opposite. all torques are equal and opposite because it's torque that changes angular momentum. I'll put that in a minute. And by a very similar argument, you find that angular momentum has to be conserved in any closed system. Okay. The other quantity is torque. And we talked about that last week. Just to refresh you. Let's just say I've got this beam rotating about its center. And I exert force here. My R vector goes from the axis of rotation out here. Torque is a cross product of R with F. What's the direction of the torque? Well, cross product R cross F, you put your fingers in the direction of R so that you can bend them toward F. So the torque is into the board. Make sense? Another way of saying is this force exerted here would tend to rotate the thing clockwise. So you got clockwise rotation, put your fingers around that rotation and you get the same result, that the torque is into the board. Okay? Analogous, the force equals mass times acceleration. You have torque equals moment of inertia times angular acceleration. Newton's second law for rotation. I'll develop that for you a little more, but I want to give you enough overview to do some of the problems I'm going to assign. Okay. Now, if I exert the torque on this system, it's going to tend to change. It's going to result, if there's a net torque on this system, and better write net there, add up all the torques. Friction's exerting a torque opposite to motion. And that was a little hard to get a handle on for this system because it's very low. And it's down there in the bearings. And it isn't all that constant with velocity. Okay. But anyhow, if you know the angular acceleration in the initial angular velocity, what can you find? Well, if you know the time during which that angular acceleration occurred, you could say that change in omega equals alpha bar delta t. Now let's suppose that I've got that bar held out far enough that I don't lose the tip of my nose or knock my chin off. And the thing is rotating like this. Okay, it's rotating fast. Faster than it would be safe to get close to it because it's metal and it's got kind of sharp edges. Okay. Rotating like it's like crazy. Okay. So it's angular velocities in this direction. Now let's say I've got this thing, let's say the axle is something I can grab onto so I can move it around. Okay. Now let's say I move the axle like so. Okay. Then I've applied a torque to the system, haven't I? What's the direction of that torque? Well, the torque would tend to rotate this thing in this direction. Make this thing move and spin in a circle like this, right? So we'd be moving the circle from here to here. Okay, can I do that for free? Well, no. Because I'm exerting a torque on something with a moment of inertia and I'm getting an angular acceleration that's in the same direction as the torque because of course the moment of inertia is just a constant and it's a positive constant. So that the torque is parallel to the angular acceleration. Okay. And of course, angular acceleration is then parallel to the torque. So I exert this torque. Now, what's the direction of that torque? Well, I'm tending to rotate it in a circle like this. I could do my R cross force, but it's this way. So the thing is rotating in what direction? This direction. Right hand rule. The torque is in this direction. Okay, so angular velocity in this direction, torque in this direction. What's that mean? That means you have an angular acceleration in this direction. You have an angular acceleration in this direction and an angular velocity in this direction. What's going to happen to that angular velocity? We're moving this direction. You got a torque here. Alpha is here. Delta omega is in this direction. And I said torque. Okay, again, spinning in this direction, in this plane. Counterclockwise gives us a torque in that direction. I mean, gives us an angular velocity in that direction. So omega is in that direction. I've got the thing here. Rotate it this way. There's a torque. Giving you a moment, giving you an angular acceleration. And expand the picture a little bit. Torque in this direction. Angular acceleration in this direction. Delta omega in this direction. So I've got my omega, which is a vector. All these are vectors. Omega here, delta omega here. Final omega here. call this omega naught. That's the omega we have. This thing's spinning before I try to turn it. When I turn it, I'm not going to be able to turn it really fast. If I try to turn it really fast, then my delta omega, well, I'm going to need more torque, which gives me greater angular acceleration, which gives me greater delta omega, right? Which means that this delta omega might be a lot bigger, or for a small time interval, it might still be this much, but in a small time interval. I'm not sure that made a lot of sense. The point is that what I'm going to feel when I try to turn this is it's going to want to go up this way. So instead of being able to turn it and keep it in a plane, I'm going to be turning it and it's going to want to twist. That makes sense? No. Not until you've had the bicycle wheel in your hand and tried to change its direction. I've got to try to bring the bicycle wheel because I think I didn't put it in storage. I think I took it home and put it in a safe place, which means I'll never be able to find it. It's pretty big. I lost it back in that little room back there that was about this wide and as long as, it's back in the corner, perfectly visible, but I couldn't see it. So it keeps escaping me. I've got other things we can use that with, so we'll do that in lab. We'll get the thing spinning that way. You can hold it, then you try to turn it. And it'll pull you up. Principle of the gyroscope. With the gyroscope, you just mount the thing on good bearings, gimbal bearings, so you can rotate it, so it can be rotated in any direction. So now if you're out in space and you have this gyroscope and you got it well mounted, it's going to always point in the same direction. Angular velocity is not going to change because there's no force on it. So you always know where you are, at least in what direction you're moving. Because the thing will appear to rotate as you orbit the Earth, let's say. So if you can't see the ground, one reason or another, maybe your windows are all fogged up or something. At least, when you come back to the place where you started. Okay. That's kind of where we need to get in this chapter. Now let me explain to you how I've arranged the problems, because we need to be finished with this chapter and actually started with the next by the first of next week. Okay. I believe there were roughly 6 problems from each chapter that I was still going to assign. 6 more from chapter 9. Okay. Maybe 2 sets of 6 more from chapter 10. And 6 more from chapter 11. Well, I picked 2 from each of those sets, and that's what it'll be due Wednesday. Okay. Then there'll be the other 4 from each of those will be due on Monday. You did have some initial problems in chapter 11 due today. I haven't looked at them yet. Like I say, the chapter 9 looked pretty good. I had to complain about things like units, I always do, and other things. People seem to do fairly well on the last few problems, which are a little more challenging. Okay. So we'll see what we get Wednesday. Read your book. Try to sort this stuff out. Again, the point is angular momentum is I omega. It's a vector. In a way, in an argument similar to the fact that interacting particles exert equal and opposite forces So they have equal and opposite impulses. You get equal and opposite torques when two rotating things interact. Okay, which gives you equal and opposite changes in angular momentum, which means angular momentum is conserved in a closed system. That's real important. As an example, that spacecraft you're about to crash into Mars, okay, well, it started its life in kind of an eccentric orbit around the Earth, and that got boosted into an orbit kind of where the sun took over, okay? But Earth is at the focus of an elliptical orbit, okay? So we get an elliptical orbit moving around this focus, and it's eccentric. It's closer in here than it is out here, okay? It's got an angular momentum out here. It's got an angular momentum in here. It's equal to your R cross V up here. It's equal to your R cross V down here. Much smaller R, much bigger V. Much bigger R, smaller V. Okay, give you the same angular momentum. Just another example of conservation of angular momentum. Then we got the definition of torque. You just got to keep in mind where these vectors are and keep thinking about it. Start with the right-hand rule, but these things add as vectors. Typically, your angular acceleration vector won't be in the same direction as your angular velocity vector. And then you got to think about what's going to happen. Okay, well, good luck with that. But those are the principles. And I'm not asking you hard problems about angular momentum conservation this time. You have those to look forward to over the weekend. Okay. I'll see you Wednesday.